Hello and welcome to the domain and range of a function. Thank you very much for showing up for your learning once again. Today we will be looking at these particular characteristics of a function. Domain and range. So let's copy some definitions on your sheet. So I have my sheet over here. Here it is here. And I'm going to get ready to take a look at some key definitions, domain and range. And then you're going to copy your definitions down here. All right, so let's go take a look. The domain. The domain is the first set of coordinates of an ordered pair of a relation. These are the x values. Okay. Now, what are we talking about when we're talking about the domain of a function? If I have this function here, given by this table of values, first of all, is this a function?
Yeah.
Wow, how do you know, Rylan? There's no repeated x's, so it is definitely a function. Very good. And the domain of this function would be x could be 0, x could be 2, x could be 4, x could be 8, or x could be 10. Okay, those are all the possibilities. And then if we take a look at what we had over here for marks, sorry, I said I was going to willingly deface it because we weren't going to need it again, but here I am going to reference it again. We have the line, which is average number of marks. Okay, this was a function, and we know that passes the vertical line test. It was the average mark that you would get given the amount you studied. Here, our domain, we have 2 and 2, so that repeats, it's not a function. We have 10, 10, 10, repeats, not a function. Again, a vertical line would hit all those points. And 20, 20. So here, our domain would be, and I'll get a little bit ahead of myself, but the domain would be x is of the integers, colon, x is equal to 2, 10, or 20. Okay? And then I could have that all in little squiggly brackets there. So that would be the domain of that function. X can either be 2, 10, or 20. It can't be other values of x. Okay? Now the domain and range of this function here, the domain, would be x could be actually of the real numbers. It doesn't have to be an integer. And x could be anything bigger than 0. 0 or bigger. Up to infinite values of x. You study an infinite number of hours and get an infinite mark. Maybe there's a point at which you would cap that. Maybe you would cap it at the total number of hours in a week.
Yeah, because technically it's not infinite for that because you can't study more than a certain hours a week.
Yeah, sure. So we might say it's up to a reasonable number, like maybe 30 might be an upper end for amount of hours you could study in a week. Or like 40 would be studying 8 hours a day for 5 days.
Yeah, so you'd be like, get home from school, study till like
midnight. 11 or something, yeah. Okay. So anyway, those are some ideas about domain. Domain is just listing the total possible values of x, all the different things that x could be for a certain function. And then range, range is how much can the function range? Given that it's domain, it's like where does the function live along what values of x? So you can think of like the domain of lions is the Sahara, and they live in the Serengeti, and that's like the horizontal space upon which lions live. That's their domain. That's where they live. Where do they range? How high do they range? How low do they range? Is about the y's. So the range is the second set of coordinates. It's the second set of ordered pairs. Okay, so all of these would be the range of y. And this focuses on how far up and down the function extends. So this function can output something as low as -1 and as high as 5. And it seems to only output values of 1, 5, and -1. So this is a list of its range. All right. Now, when we're notating this, when we're writing it down, we use these conventions for writing it down. You'll notice I've highlighted those there. Okay. Now we say the domain is x, and so it's about the x values, and x is of the, and then we need to say what number set that x is of. So what are the number sets? Okay, number sets, and then we also talk about restrictions on the domain here. So you'll notice that I've used that notation over here where I've said x is of the integers, and x is equal to those three things. So there's the limitation on x. Now, when we read this is the way we read it. The domain or range is a set of values of x such that x is of the, and then we're going to say the number set. and x is blah, 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 blah. So we have to know how to read these out when we see them. So let's take a look at what those number sets are. And we're basically looking at two number sets in this course. There are other number sets, and we can bring these number sets down a little bit more carefully. But basically, there's the integers and the real numbers. Integers are all the whole numbers, both positive and negative. So on your sheet, I would write down some examples of integers. Is negative 20 an integer? Is 37 an integer? Is 57,000 an integer? Is $5.25 an integer? How do you know? Because my voice changed, or because you know?
It depends on if you're looking at it by cents. If you're looking at it by cents, then it is.
Yeah, if I was like number of quarters, then that would be an integer, right? Because $5.25 would be 21 quarters. And that's an integer, 21. But 5.25 is not an integer. If it's a decimal, if it's a fraction, it's not an integer anymore. Real numbers include all integers, all terminating decimals, all repeating decimals, and repeating decimals. See? Haha, there's a joke there. The decimals that repeat. Haha. Negative 2 over 3, that's a repeating decimal of negative 0.6 repeating. That's a real number. It's not an integer. All the fractions are real numbers. In fact, the fractions create a smaller set of numbers within the real numbers called the rational numbers, because they're based on ratios, okay? But we're very rarely going to distinguish that when we're talking about the domain or range of a function. We're often going to say that this is just of the real numbers. All the reals include all the ratios. All the fractions are in here. And there are numbers that are non-fractions. Can anyone give me an example of a number that cannot be written as a fraction? 8 over 2. 4 over 1 can be written as a fraction. Siraj?
Square root of 2.
Can that be written as a fraction? Square root of 2.
Yeah.
What is it though? Well, 2 over root 2 would be square root of 2, but that's still got the root in there. So it's not like a proper rational number. Yeah. Square of 2. The square of 2 is a non-repeating decimal that cannot be written as a fraction. Any other numbers that can't be written as a fraction? I'll give you a hint. You like to eat it. It's one way we talk about pizza. Pi. Yeah, pi is also a non-rational real number. Pi is a number between 3 and 4, and it cannot be written as a fraction. Although there are some fractions that are rather close. Okay, so now let's carry on. These are integers. These are real numbers. Siraj?
Is E included?
E? Yeah, E would be a real number, but it's not a rational number. Yeah. And then phi is based on ratios, but it's based on the golden ratio, but it's also real and irrational. It's an irrational real number. But the main ones we're concerned with, you want to be able to understand what's an integer. Those are your counting numbers, including the negative numbers and including 0, are integers. Then real numbers are all the other numbers that are real, that are not imaginary. Okay? Yeah, Jackson?
How do you write 7 as a fraction?
You could write it as 7 over 1, 14 over 2, 21 over 3.
Yeah, so anything like that's divisible.
Yeah, okay.
Yeah. So there's several ways to write that one as a fraction. So that would be a rational number, but it's also a natural number. Natural numbers are your kindergarten numbers, 1 and up. Integers expands on that, adding 0 and adding all the negative numbers. Okay? So we can go forward, right? We're going to continue on. So now, ordered pairs. So if we're writing about ordered pairs and looking at domain and range, when the number sets that we're given are integers, then the domain and range are going to be integers if we're looking at a table of values. We want to arrange them in numerical order when we write down the domain and range, and we don't want to repeat values if they appear more than once. Okay? And remember, it's only a function if no x values are repeated on that table of values. So if we take a look here, and we want to write down the domain and range here, I can't write on this board, unfortunately. It's not a dry erase board. Maybe I'll
There's markers on the bottom.
those do not function anymore. They're like electronic markers. The software does not work with this projector, unfortunately. But let me just do this one on the board for you.
Negative or positive, and there's like if it's negative,
Still
one
a function
positive.
because it's
Yeah,
the
that would
same
make a
y
difference.
value, it's different x's.
Yeah, same y value, but different x's. So that can still be a function. So I'm allowed to repeat y values. It can still be a function. Okay? So here for my range statement, I have y is a set of values such that y is of the integers and y is equal to, and I'll arrange them from smallest to lowest. I see 2 twice and 5 twice. I only need to write them once, and then there's a 3. So it's y is equal to 2, 3, or 5. And then I close my squiggly bracket. Okay? This passes the function test because in the domain, there's no repeated values of x. Okay? Now, let's do the next one. For b, and I'll use a different color chalk, just because I have access to other colors of chalk. So here, I have my value for the domain. So to do the domain, I write a squiggly bracket, and I say this is a set of x values, such that x is of the integers. I'm not seeing any real numbers there. I see no decimals, I see no fractions. So they're all integers. So I can list that x is of the integers. And x is equal to, here I have -5, 2, 1, 8, and 9. -5, 2, 1, 8, and 9. So I have x is equal to -5, 1, 2, 8, and 9. Is that a function?
Yeah.
Yes, no value was repeated. Great. The range, I do squiggly bracket. Y is a set of numbers such that y is of the integers, colon, and here are my restrictions on y. Y is equal to, and I list them. I have 6, -5, 9, 2, and 1. 6, -5, 9, 2, and 1. So I have -5, 1, 2, 6, and 9. Just writing them down in numerical order. Did I miss any? No, I got them all. So that's how I write the domain and range for these sets from tables of values. Jackson.
So the first one, that would not be a function, right? Because it repeats itself.
No, there's no x values that were repeated.
Oh,
-1, 1.
Yeah.
So -1 is quite different from 1. It's, it's two different.
Yeah, let's say it was 1 and then another 1. So that would be a function.
Yeah, if I did so much as this, if I just covered that up, now not a function.
Yeah.
If that was 1 and then there was another one, not a function anymore. It's a relation. You're still going to study that. But when we're working with functions, those are some of the qualities that we need to identify a function. Brian.
The thing at the beginning, the x, whatever x.
The squiggly bracket? Oh, the D and the R?
No, the line thing.
Oh, this?
Yeah.
What is
That's the
that?
whole thing with the x and the y and the x and the I don't know what that.
Oh, yeah. So this is like, the domain is a set of numbers, a set of x values. Okay, and I'm going to indicate x there. Later on, for like my independent variable, I might have time. I might have years invested money. I might have frequency of a note played on the guitar or something. I might even have the club that I'm hitting. If it's like a 5-iron, it goes that far or something. And I have a function based on the club that I hit and how far they go, maybe. Okay, and what am I talking about? Right, so I'm going to indicate what I'm gathering there. What are these values? In these cases, they're just x values. X is a set of numbers such that x is of the integers. This symbol that looks like an E means of the. It tells me what set of numbers that x is from. And then I have a colon, and after the colon, I put the restrictions on that value. So here, I know that x is quite restricted. There's only 5 possible values it could be. And so I list them there.
And then that line you said is such that. That's
Yeah,
what you
yeah.
okay.
It's a collection of x values such that x is of the integers and this is all true. All right, let's carry on.
Wait, why? Back to domain and range.
Sorry?
Can you go back one?
Yeah.
Just a slide.
Uh-huh.
For
So that's a good question. For this this one here, for y, why do we only have 3 numbers over there? And the reason is we only have 3 numbers over there because, if I duck, you can see it. We only have those 3 numbers Because they're repeated. See, 2 shows up twice, 3 shows up once, and 5 shows up twice. So that's why we just write each one once. We don't have to write it's of. Yeah. Okay. Okay, carrying on. So now we could do the domain and range of this. We could read off of a graph and find the domain and range of this. Is this a function, these 4 points? Think of vertical line test whenever you see a graph. Can I put a vertical line through any 2 points at the same time?
No.
No. So is it a function?
Yes.
Yes. Okay, good. So this would be x's of the reals, x's of the integers, such that x is equal to -5, -1, 2, and 4. And y is a set of numbers such that y is of the integers, and y is equal to -4, -2, 1, and 3. Okay, that would be how I would list the domain and range for that one. But let's keep going. Yeah. Okay, now, if we have a continuous graph, it's a little different to take a look at the, what's going on with my cursor? Right there, that's why I do it. I need to think about how to do domain and range for continuous graphs as well. It's not possible to list all the values here because the graph's continuous. It's made up of an infinite number of points. Think about a line, think about a parabola. In the example we had of hours studied versus mark received, we only had 3 values of x. There was x's of the integers, and x was 2, 10, and 20. Maybe that was the way we conducted the study. Do you study an average of 2 hours a day, 10 hours a day, or 20 hours a day? Pick the one that's closest. Then all of our values would be either one of those 3 after we gathered the information from that study. Okay, from that survey. But the line, we could use the line to predict what your mark would be if you studied 2.5 hours, 3.25 hours. There are an infinite number of data points that line can predict. 1.1113 hours is still on that line. So we need another way to write continuous things, and we use interval notation to help us describe the domain and range for graphs that are continuous. And to be honest, this is what we're going to be spending more of our time on, is interval notation. Okay? So let's go. And remember, it's got to pass the vertical line test to be a function. So let's go forward and take a look. Here is a graph. It's a line, and it has 2 endpoints. We're noticing the endpoints there because we're seeing the little closed dot. The closed dot, when you see that on a function, it means including that point. Okay? So here, we have to identify the far left and the far right x values and the highest and lowest y values. And then we're going to say, what's the value of the function in between there? So let's write this one down on the board as well. I'm just going to make this big for those of us at home. Okay, so we want to write down the equation for the domains and ranges here. So I'm going to use this yellow one. I'm just going to remove all this data because the rest is going to be the same. Okay, so now, if I'm talking about the domain and range of this function that I'm seeing, I would say x is of the, do I say integers or reals here? Reals, yeah. Because as I look at that picture here, I see that x can be values that are in between integers. X can be 1.5, -1.5. X can be 1 1/3. You know, it can be all of those possibilities. So we say x is of the real numbers here. Big distinction. Yep, Owen?
So if it's a solid line, can you keep up? My name's Cole. Not
Oh, I'm sorry,
It's okay,
Cole.
don't
Yeah.
worry about it. If it's a solid line, then it's real numbers, but if it's individual points, then it's integers, right? Like if it's individual points on a...
Yeah, if we were looking at a line that was only integer points, it would actually be represented by dot down there.
Instead of an actual line.
Yeah, that's right. Yeah. And we can join those, as you say, with dotted lines to indicate, look at the line that these dots form. Yeah. That would be like your money invested at 10% simple interest, and they only pay out once a year.
Yeah.
So it's not like it's continuously growing. It's like it grows like a step ladder,
Yeah.
So it's always on an integer point. Yeah. X is of the real such that, and then we want to indicate the largest value of x and the smallest value of x. So the smallest value of x here is -3. -3 is less than or equal to x And then I'm going to write the largest possible value of x, which is here 5, is less than or equal to 5. Okay, and then I close my squiggle bracket, and I'm done. So now, what I want to highlight here is the use of greater than or equal to signs here, and less than or equal to signs here. So what I'm saying is x always falls between these two numbers, including these numbers. Okay, including those numbers when I have the less than or equal to part of the sign there.
That line.
That's what that sign's for. And that indicates that as far down as -3, you will find x values for that. You see down there -3. -3 in the x. Okay? Including. And the reason it's including is because it's a closed circle. All right? Now, if we do the y, so the range, we're going to say y is, the range is a set of y values such that y is of the integers, sorry, y's of the reals here, because again, y could be any fraction in between. And we go with our smallest value of y, which is 2. 2 is less than or equal to y, is less than or equal to, and our highest value is 4. And then I close my squiggle bracket. And that gives me the domain and range for this function. And I can read that off of the graph.
So range and real numbers are both the same, like, letter then, obviously.
Yeah.
So there's no like lowercase and uppercase, like they're both just.
No, that's a good question. I don't think so. I don't think there's a convention to write domain and range in lowercase letters. But real numbers, I certainly am used to seeing that as an uppercase R. Okay, so let's carry on. So now here's a graph with one endpoint. All right. So now I want to use these symbols to indicate that this goes continuously that way. Okay. So now let's do the domain and range of this one in purple underneath. Again, we have integers or real numbers on this graph.
Real number.
These are real, yeah, because it's a curve. Anytime you see a curve with continuous data, it's going to be of the real numbers. So here, x is of the reals, such that, so x is a set of numbers such that x is of the reals, and we have the minimum value possible of x is -1. All right. So this is -1 is less than or equal to x. Is there any upper limit on how big x could be with this graph?
No.
I see some heads shaking. That's good. How do I know that?
There's an arrow.
There's an arrow, and it says keep going off to infinity and beyond.
How would you know if there was a list?
Like if there was an arrow and it's not.
Yeah, you would have to show the endpoint. Yeah. Or if you knew practically that there was some endpoint from an application, you could indicate that here. Okay, like number of days worked per calendar year. The upper limit would be 366 because of leap years.
Yeah.
Okay, so here, and then the range. Well, also there's some limitations on the range here. What's the minimum value that can be in the range here?
0.
Yeah, 0. The smallest this ever gets, the smallest y value, is down here at the vertex at 0. This is a parabola that opens upwards. So it's like a bowl collecting rain. It therefore has a minimum point, the point where water would go first. So we would say y is of the reals as well, such that 0 is less than or equal to y. Okay, and that's how we can indicate the ranges and domains for this one. Notice
So it's all
that these don't have an upper limit.
yeah.
We just don't need to write that. It just goes on. Just this says -1 is less than or equal to x, or x is greater than or equal to -1. We could write it the opposite way as well. All right. So now, carrying on, here's a graph with no endpoints. Now, here we can do this one as well, but we'll just talk through it because it's very similar. Here, the domain is x is of the reals. And that's all I need to write. X is of the reals. And x could be equal to -infinity or positive infinity. This graph goes off in both directions. Right?
Yeah.
So we would just write this. X is of the reals. Done. Okay, it's of all the real numbers. We don't need to have any restrictions. There's no restrictions on x. Are there restrictions on y here? Yeah, what's the restriction on y?
9 and negative 15.
Yeah. So the minimum value that this could be would be negative 15. What's the maximum value?
9.
Really? What does this arrow tell you?
Oh, it's unlimited.
Yeah, this tells you it goes off in that direction, right?
Yeah.
So this could be, you see how it has 1, 2, 3 turns on it? This could be some kind of x to the 4, okay, to have that many turning points. A y is equal to x squared, or an ax squared plus bx plus c, some quadratic, will only have one turning point, one vertex. You add 1 for every power of x bigger than that. So an x to the 3 could have 2 turning points, an x to the 4 could have 3 turning points like this. We won't study those, but you'll want to be able to say the domain and range of these. Okay, so here we would say y is of the reals such that negative 15 is less than or equal to y. Notice these closed circles show me that it indeed does touch down at negative 15. Okay, now let's move that bit and then take a look at this. Now, asymptotes. Asymptotes are going to be something that we're also going to indicate when we are looking at the domain and range for things. So let me go back here. Asymptotes are lines that the given curve approaches but never touches at any distance. They never quite approach, okay? So the function can never take on the value of the asymptote. Let me give you an example. On Desmos, oh, he's always going to Desmos to show us interesting things. Let me show you a function that we talked about in the morning. Y is equal to 1 over x. Notice here this function. This is called the reciprocal function. And here, whatever value of x I choose, y is the reciprocal. 0, x is equal to 0 is called an asymptote of this function. And x is equal to 0 is another word for the y-axis. Why will this function never touch the y-axis? Why does this function not have a y-intercept? What's the value of x at the y-intercept? 0. What would happen if I input that into this function?
Wouldn't it reach it like eventually?
Y is equal to x to the negative 1 over x.
Oh no, wouldn't it always stays at 1? Like, wouldn't it eventually just go vertical and keep going?
It gets really, really, really close to vertical, doesn't it? Yeah. But actually, this function still passes the vertical line test. Even though it approaches a vertical line, it never becomes a vertical line. It always has a slope. It's always getting closer, but never touching 0. Because, Siraj?
If you're dividing by 0 and you can't divide by 0.
You can't divide by 0. You just can't do that. Here, I'd have a pizza and I cut it into 0 pieces. What? You just broke the universe. My brain just reels at the possibility of cutting something into 0 pieces. Because it starts as 1. You can't cut it into 0. So, when we divide by 0, we lose all kinds of legitimacy, credibility, whatever. We can't do that. But we can get very, very close and notice extremely small values of x give us extremely large values of y. Extremely large values of y, extremely large values of x give us extremely small values of y. Okay, so that's this picture here. This is the reciprocal of just the line y equals x. Different, eh? So anyway, let's go back to our PowerPoint. So when we're doing the domain and range, we need to indicate where our asymptotes are. Asymptotes are lines, like that line x is equal to 0 there, where the function has no value. It's a limit on the value of the function. Actually, the range there for that function would be x is of the reals such that x is not equal to 0. Because if I go back to my picture again, x could be any value, any real number, but not 0. Only 0 is the only thing x cannot be. And I can put any other integer or real number under there for x. And it still computes unless I put 0, at which point your calculator says error, and the universe groans with the paradox. Okay, so let's carry on. So that's the definition of an asymptote, a line that a curve will never touch. Okay. Sure. Yeah. Now, here we have another example of a function with an asymptote.
Can you go back for a quick second?
Sure. Yeah, so go ahead and copy. I'll give you a minute. So here, if I'm writing down the range of this function, sorry, the domain of this function, I would say, so I'm going to do this up here. Let me just make this bigger so people can see if you're way back. Here we go. Boop, boop. All right. So now I'm going to do it up here in the yellow. And I'm going to change these because the rest is going to stay the same. Both x and y are of the reals, so I can still use that. But x is such that x can be any value of the reals going towards negative infinity or positive infinity, but x cannot be 2. So x, and then I just indicate that x is not equal to 2. All right? Now, when I say x is of the reals, that means all the way from negative infinity to positive infinity. But x cannot be 2. And then y also has some limitations on it, such that y, it looks like the x-axis is also an asymptote for this function. And that as y gets smaller and smaller, it will approach but never touch the x-axis, is the assumption we can make from this picture. If x goes towards positive infinity, y approaches but never touches 0. As x goes to negative infinity, y approaches but never touches 0. So there, we actually have to say y is greater than 0. We do not say greater than or equal to because the 0 is the asymptote. That make sense? So I have to use this notation instead of greater than or less than or equal to type notation. And then I close my squiggle bracket. Done. Okay, so that's that example with an asymptote. All right. Here's another one with an asymptote. Here, I'll just verbally tell you. This would be x is of the reals such that x is not equal to 2, and y is of the reals such that y is not equal to negative 1. Okay, because those two lines are asymptotes, both in the x and the y.
Y is not equal to 1, not negative.
Negative, yeah, y is not equal to 1. Thank you very much. Yes, I have a sign error there. Y is not equal to 1 because y cannot become 1. Y is negative 1 right there, so I would be a liar if I said y cannot be negative 1. Okay, if I wanted to have a little gap in there, I can put an open circle, and that would indicate not that value. Now let's take a look at the domain and range handout on the hovercam, and we'll go over these examples. So take out your handout. We'll talk about them as a class. So here we go. Here is the handout of which I speak. All right, it is this one, domain and range. Let's zoom in and get it nice. Hi there. And we'll go over these examples together. Okay. So here, I'll do the first one, and then you can shout at me for the next ones. I'll do the first two, actually. Here, the domain is such that x is of the reals, and x is any value 5 or less. So I would say this is the domain is a set of x values such that x is of the reals, and colon, x is less than or equal to 5. Okay, less than or equal to 5. You'll get used to me making so many mistakes like this so often. I should work in pencil. I don't do my crossword with a pen like Confucius does. Less than or equal to 5. You see, it's any value less than or equal to 5. The range is a set of y values such that y is also of the reals, colon, and then I say I see y as 2 or less. So 2 is greater than or equal to y. All right. 2 is the bigger number. Y is going to always be less than 2 unless it is exactly 2. Okay. Now, over here, I have open circles. When you see open circles like this, they indicate that that value is not included. I have to exclude open circle values. Okay. So here, let's label this point. That looks like the point negative 5, 4. So write that point down if that helps you. Negative 5 in the x, 4 in the y. And over here, this is negative 2 in the x and negative 4 in the y. All right? So if I want to list the domain for that function, I'm looking for its possible x values. So I would say the domain is a set of x values such that x is of the reals, and x is greater than -5 and less than 2. So here I need to write this way, and I'm going to write it up here because I just don't have enough space to do it down here with my clumsy hand. So I would have -5 is less than x, but x is also less than -2. Okay, and then I close my squiggle bracket. So let me do that just as a big one up here. The domain is a set of x values such that x is of the reals, and then I have a colon. My goodness. I need to blow this up bigger for my hands. Yes, sir.
The E is for equals. What's the E for?
Oh, it indicates that that is of the set of those numbers. So we say x is of the integers, meaning x is a set of integer values. All of these are continuous graphs, so they're all of the real values, of the real numbers.
All right.
Okay.
Yeah, thank you.
Okay. Now, here I have to use less than signs, because it does not include these points. I don't use less than or equal to, because these are open circles. Here's an open circle that goes off to infinity. So what would I say the domain is for this function?
Well, it is a function.
Yeah, it's a function. X is of the what? Integers or reals?
Real.
Reals, such that x is equal to or less than or
Greater than 0, right?
x is greater than 0, but it also wants to be these values too, all the way down to here, but not including that value.
But it does not equal, is that -1? I can't read it.
Yeah, that's -4.
Oh, -4. It does not
It is greater than -4.
Greater than -4, that's right. So x is greater than -4. Yeah. And so that tells me from there and all the way out, all those values, but not that value.
Wait,
And
what
I-
about the range for that one? Why didn't
What do
you
you
do the
put in
range?
the range?
Oh, so the range here? Oh, because we're short on time. That's why I didn't do the range.
Oh, it's the same with
Okay.
the other one?
So down here, the range is going to be from here up, right? So y is a set of numbers such that y is of the reals and y is greater than -1. Y is greater than -1. Okay. There's my statement for the y values there. Okay. So do people want to take up a couple more examples here, or do you want to get working into it on your own?
One more thing.
One more example. Here, is this one a function?
No.
No.
No, it's not.
Why not?
Has the vertical line.
Vertical line fails the vertical line test, therefore not a function. But it still has a domain and range. Okay? So here, what's the domain of possible x values? X is of the reals such that it looks like -5, but actually this keeps on going that way. Yeah. What's the biggest x could be?
Equal to or less than 3.
Yeah. X is less than or equal to 3. Yeah, and that would be my domain statement. My range would be similar, but it would start at 2 and go up, because this arrow is going up to infinity in the y as well as in the x. So there I would say y is of the reals, and y is greater than or equal to -2. And those are domain and range. And that's how we calculate the domain, or how we read the domain and range of various functions.
Can you just fill in that range at the top so I can copy it?
Oh, sure.
The second one?
This one is y is of the reals such that 4 is greater than y, but y is always greater than -4. Okay, there.
And then there's a colon in between the R and the 4.
Yes, thank you.
Is that a -23 or is it just -3 or 2?
-2. That's my squiggle bracket.
Is there any homework tonight?
Yeah, so let me wrap this up here.